Let me welcome you to the 46th lecture of NPTEL online certification course Drilling and Blasting Technology. So, this lecture will be on impact of rock and rock mass conditions on drilling and blasting. So, before that we have carried out some exercise on the drilling costing, blasting costing. Prior to that we have carried out understanding of the performance of the drilling and blasting operations, their designing part and the basic technology of drilling and blasting. So, we have discussed some part of the rock and rock mass to be excavated by drilling and blasting, that is we have already carried out what is rock and rock mass, we understand that because of our previous lectures. We have also discussed some part of the impact of rock properties on drilling operation like drillability etcetera, we have calculated, and we know different drilling techniques. Introduction to blasting is also known to us. In this lecture, we will try to understand the impact of rock and rock mass properties on blasting. That means, how the different rock and rock mass properties, that is the strength of the rock, joint set in the rock mass, joint details and other impedance matching etcetera, are basically influencing the performance of the blasting, because that is an important parameter should be considered while we are carrying out blasting in the rock. So, first is that how we are considering rock or rock mass for the blasting. Basically, in blasting rock and rock mass, we are considered as the medium. Which type of medium it is? The purpose of blasting is to fragment the rock mass, and rock mass is the medium which is basically allowing its own disintegration by propagating the explosive generated energy. So, basically explosive generated energy which is propagating through this rock medium, and its propagation, during its propagation it is basically fracturing or disintegrating or fragmenting the rock. That is the way basically the rocks are fragmented in the blasting. So, basically rock is acting as a medium here, and explosive is the source of energy which allows the medium to be fractured or medium to be broken. So, basically you understand it is basically depending on the energy transfer from the explosive to the medium, and that is why this understanding is very, very important. But prior to that, let us observe this video. In fact, I ask all of you to observe this video, this is very, very important. There are many videos, this video link, YouTube link is already given. There are many videos available in the YouTube, because every time doing so, some understanding, some observations are found. See here, this is a high speed photography showing how the bench is being moved in the blasting operation. So, that is the requirement of understanding how the blast is being propagated. There are different rock condition you can see. This is one type of rock condition, previous one was different, but I would like to put you into this. You can see the rock condition here. So, in this rock condition you can see these are the joint sets, these are another joint sets. Okay. Obviously, there are many other joint sets are there. See, these are the joint sets. So, multiple joint sets are existing, and if you see the above one benches, you can see the excavation has carried out this way, again this way, again this way. So, like that way there are possibilities that the proper bench forming or proper wall rock forming may not occur if the suitable blast design is not made. So, that is why understanding of rock mass and rock mass properties are very, very important. So, let us look the blasting of this one. Okay, once again let me put it in. Yes. So, this is, you can see the fragmented rock mass has come out from those, out of those joint sets, and that is fragmented there. In the next picture also you can see another one. See here, you can see the wall rock, how this wall rock is there. See, these are the likely chances of forming. There are different joint sets, and the proper positioning of the holes are very important here to have the proper fragmentation. So, basically that is why the understanding of rock and rock mass properties are very, very important for blast design, and here in this lecture basically we are trying to see how these properties are influencing the rock mass. But prior to that, let us understand what are the rock properties we are interested for. So, these are the some of the rock properties. You can see, one is that suppose there is a, this is the bench we would like to blast. So, if you are considering this is the bench, you can say there are different layers. This is one layer, this is another layer, this is another layer, this is another layer. So, there are many layers of rocks are available, and these rocks are having different strength properties, different dynamic properties. So, that has to be considered while we are carrying out design for this. Apart from that, you can see there is a fault plane in this. There is a fault plane in this figure. So, if we are carrying out blasting for this particular benches, we have to consider this fault plane, how this is occurring. This is in this figure also you can see this is a different types of layer, this is different type of layer. There is a small layer maybe of very weak or strong. So, that has to be considered while we are designing our blast hole, and we have to place our explosive accordingly. Okay. So, that is the very important aspects in the blast design. The theory of blasting designing what is discussed in our previous lectures, there we have not considered any such conditions, we have not considered, and that is why this in this lecture or in coming 2-3 lectures also we will discuss how these rock properties are basically influencing, and based on that what decision we have to make to cater this occurrence of the different layers, in that is the heterogeneity in the bench formation. Okay. So, the first important parameter is the transfer of the explosive energy from the explosive to the rock, and this transfer is basically depending on the impedance of the explosive and the impedance of the rock. So, this impedance is basically nothing but the explosive impedance is nothing but the multiplication of the density and VOD, that the product is considered as the explosive impedance. For the rock, it is the density and the p wave velocity of the rock. Okay. If it is the case for a particular rock mass where the blasting is carried out, then the p wave velocity of the rock mass must be considered as the impedance. Now, generally what is happened, rock impedance is density of the rock is also high, the p wave velocity of the rock is also high, and density of the explosive, you know, it is closely nowadays that ANFO emulsion slurry, those which we are using, ANFO is less than 1 and specific gravity less than 1, and for slurry and emulsion it is close to 1.15 to 1.2, something like that. So, the density is also very less, and the VOD we need very high for the explosives to match this one, but often we do not get very high VOD for emulsion, slurry and ANFO, those are coming close to 4000 or so. So, that is why generally the good VOD is wanted from the explosive, so that we can match this one, because the rock density is higher, almost double than the explosive density. So, to cater that problem, we need to have the higher VOD of the explosive, so that the maximum energy from the explosive to the rock can be transferred. So, you understand basically this is the seismic energy which basically transferred in form of the wave, and this wave propagation is basically controlled by the Snell's formula. So, that is why this is basically that Snell's formula we are using here for the understanding the transfer of explosive energy from the explosive to the rock. Apart from that, another point is also very important here, that whether our charge is decoupled or not. If we are using bulk explosive, then the explosive is directly in contact with the wall of the rock, wall of the hole, that is the rock. But if we are using cartridge explosive, then the cartridge is lying in the middle and there is a gap between the cartridge to the rock. So, that means this air gap is basically there. Obviously, while stemming some part may be filled, but that is of very low p wave velocity. So, there is a change in the medium from this to this, then this to this. So, this change in the medium basically result into the loss of energy, and that is why the proper energy transfer will not be achieved using the decoupled charge using the cartridge explosive. So, that is why basically we want that the bulk explosive should be there, or it is completely fully coupled charges must be used for the blasting, for the better transfer of the energy from the explosive to the rock. So, this is one part, the explosive energy should be transferred to the rock properties, this we have discussed earlier also. But our idea is that how to position the explosive inside the hole. So, first let us consider that we are having a homogeneous bench. So, this is the homogeneous formation. So, in this homogeneous formation, the complete rock is same, this type of rock is there. So, in this case generally we prefer to have a single column of explosive, we detonate that and blast it, we are having a proper stemming height, we are having a proper explosive height, we design the explosive VOD etc., so that the explosive energy is sufficient to fragment this part of the rock. So, that is the easy calculation, easy understanding that is carried out for a homogeneous bench, and in homogeneous bench we must use a single column explosive, we must use a single column explosive for blasting. This concept is good if our hole length is not significantly high, but if we are having very long holes like say dragline benches etcetera, where we may have a hole of 30 meter or so, in those case we may consider of separating the charges in phases inside the hole. Otherwise, generally we want a single column explosive in a homogeneous bench formation. Okay. So, this is the homogeneous bench formation where we want a single column. This design is also easy and we expect the result is also very good here. But if we are having two different types of layers, as we have seen in our earlier figure, this two different types of layers, if these are the cases, then we have to reconsider our design. So, there are many possibilities there. This top layer may be of significant a little bit say softer formation than the bottom one. So, in that case we may not require anything to change, a judiciously single placing of single column may be sufficient for carrying out this blasting. In this case it is expected this is a very strong, this is weak formation. So, placing a single explosive column here is sufficient because fully explosive charge is given to this strong rock and a little bit charge is provided for this weak rock, that is sufficient for carrying out blasting in this condition. So, in this condition also a single charge column may be sufficient to carry out blasting in this. So, basic principle is that where here we are considering it is basically two different bench. So, this is one bench, this is another bench, but we are carrying out blasting. So, this explosive is sufficient for this one and this explosive is sufficient for this one. So, this is the assumption and considering this we are carrying out blasting, though it looks single column, but our basic consideration is that we are considering it is two different benches being carried out blasting simultaneously. Okay. But there may be cases where this is significantly different. This is maybe a little bit stronger rock, this is also very strong rock. So, that small quantity of explosive may not be sufficient for this. Okay. In those cases we have to divide it in two part, two benches. So, we are considering this is one bench, for its this is the explosive, this is the stemming, this is the second bench for his this is the explosive and this is its stemming. Okay. So, this is if this length is sufficient, this height is sufficient, this is practically possible, this is very good. Our considerations of the two benches with two different charge compositions are very good for blasting for this particular case. So, here also this designing is very good and we must know this concept is called deck charging. This concept is called deck charging. This is called stemming. And this is called decking. There are different concepts. In many places, instead of placing it with the same stemming material, that is the soil material or sand, that type of filling, we may have a spacer also. So, we may have spacer here also. Okay. So, then also it is called decking, but in that case if you are using a spacer, then it is called air decking. If you are using inert stemming material, then it is called inert decking. Inert decking. Okay. So, this terminology you must remember, this is not written in the slide. So, that is why I am describing it. You must remember that this deck charging is of two types, it may be air decking or it may be inert decking. So, depending on your suitability, one can adopt this one. There are many concepts, some people argue air decking is better than inert decking, but I am not in a position now it to claim the originality among these, okay. But there are many claim on that. Okay. So, this is my concept. I am not currently voting for the inert decking or air decking. So, whatever it is, these are the available technologies. Okay. Now, here the important part which I would like to draw your attention, that how you will initiate these two charges. This is charge 1, charge 1 and this is charge 2. Now, you must be very careful here that our always initiation system should come from the bottom to the top. So, the bottom initiation has to be carried out. So, the first blasting has to be carried out in the bottom one, then the top one. Now, again if you are having a significant time gap, then what will happen? This part will be blasted, this part will become hanging one, then it will fall down and the explosive at this place will be not of use if the bottom part will be blasted ahead. So, that is why we want almost simultaneous blasting of the top charge and the bottom charge, but bottom charge may be a 1 millisecond ahead of the top. So, to achieve this one, what we need to do? We have to initiate this one. So, this figure is given for the nonel initiation system. So, this is initiated by the nonel primer, first primer is initiated by the nonel, then the second primer is initiated either by a detonating fuse from this to this. Okay. So, we basically draw the initiation from the bottom to the top using a detonating fuse or so. Remember, there should not be any delay. There should not be any delay provided between the bottom charge to the top charge. That is the essential requirement. This will ensure the simultaneous blasting. Okay. What are the other alternatives? Let us look into that also in the next slide, or let us check whether those are possible here or not. Now, many places you can see the options are there. We provide two nonels, one for the top charge, one for the bottom charge, and people claim that okay, the down the hole nonel of 250 millisecond I have provided both from the for the top and bottom. So, it will blast simultaneously, but please remember it will never happen, because nonel is having a pyrotechnic delay, and you know pyrotechnic delay has significant scattering. Say 250 millisecond nonel may blast at 225 millisecond also, maybe at 200 millisecond also. So, you do not know whether your first one will be blasted, top charge will be blasted ahead of the bottom charge, or bottom charge will be blasted ahead of the top charge because of the scattering of the nonel. So, that is why this is very problematic situation, and this must be avoided, and this is never recommended. So, this system is never recommended for the blasting, but electronic detonator is accepted because its accuracy is plus minus 1 millisecond. So, if you are giving 1 millisecond or 2 millisecond delay between these two, there will not be a significant displacement in the rock, there will not be any significant connection cut off between these two. So, all these are, there is no problem of 1 millisecond or 2 millisecond delay between these two. So, that is why if instead of Nonel you are using, instead of Nonel, if you are using a electronic detonator, then this separate initiation system for the top charge and bottom charge is accepted. Otherwise, it is not accepted and one should not go for this one. So, basic principle is that you have to consider the simultaneous blasting of top charge and bottom charge. Okay. There is another important parameter one must be careful, that is the avoiding the sympathetic detonation, avoiding the sympathetic detonation. So, if there are two charges, explosive charges, one this top charge, bottom charge. Okay. So, top charge, bottom charge, here we must provide a significant space between these two charge, and a theory is there that at least 12 d should be the length of this decking to avoid sympathetic detonation. So, that this one should not blast it, charge of this one should not blast it sympathetically, or because there is an uncertainty whether it will detonate it or not. To avoid that uncertainty, we have to provide connection between these two and it should be more than 12 d. So, any stemming, inert stemming or inert decking is provided that must be larger than 12 d to avoid the sympathetic detonation among these two. So, this is very important and one must remember this one. Deck charging basically results into the savings in the explosive consumption, because it is giving a better spatial distribution of the charge across the height of the rock or across the length of the hole. So, this spatial distribution is better by using the deck charging, that is better, and this is happened because our explosive are basically of the density matching of explosive with the rock is basically very important, and for that the explosive column we are getting is not significantly good enough throughout the hole. Often we are having the problem that our diameter which are using is more. So, the linear charge concentration is also very high, that is basically creating a situation where the explosive concentration at a particular part of the hole is basically more and it is not distributing properly across the length. So, this part is very important and one must be very careful while choosing this one. There are many other cases where many layers are there, as we have seen. In this case there are many layers. So, similar many layers can occur here and it is extremely difficult. We do not know where to provide the charge. So, here the charge is basically distributed based on the strength of the layers. So, where the strong layer, suppose this is the strong layer. So, the charge is provided associated to this is a weak layer. So, we are just providing little bit charge here, considering this part is good enough, this explosive will good enough to break this rock. Similarly, we are considering this is a strong one. So, it is mainly provided, these are also strong, but this will be taken care of this one, and we are providing a small deck charging here to properly distribute this one. Otherwise, if we are providing this one here, there will not be sufficient, the explosive column will end at this position. If we are placing this one here, then the explosive distribution in the top part will not be very good. So, basically these are the critical situations, one must be very, very careful, and that is why it is strongly recommended that prior to decide the distribution of the charge, the blaster or the blasting engineer must visit the blasting phase, see the wall rock, the photo as shown in the figure, in the video also, the wall rock, the joint sets, the layer thickness, all those must be properly noted, and based on that the decision will be taken where the explosive will be provided. So, explosive should be provided more for the strong hard layers and less for the soft layers. However, the problem occurs when you are having a strong layer, very strong layer, in the top part of the bench, because in the top part of the bench you are compelled to provide the stemming, otherwise the gases will be escape from that route and you will not get the proper gas pressure to throw the rock in the front direction. But if you are having a very strong rock in the top part, which is not significantly thick enough, if it is significantly thick, probably you would have get some explosive at this part, but it is not significantly thick. So, that is why such facilities are not available. So, that condition is very, very critical, and one must be very, very carefully design that part. And to do that, there are different ways to carry out this. In this, one very common technique is that we provide a small pocket charge at this stemming part, so that and we extend this part, reduce this explosive part, because this is the soft one and this is hard one. So, we are basically considering this is a separate bench and we are providing the charge for this particular, it may be a 2 meter bench. So, we are providing a charge for this 2 meter bench, and that is why we are reducing this charge. So, that this is considered as the separate bench and the stemming provided for this particular bench. But there is a big drawback on this, that it may throw out the stemming and air may escape, that gases generated may escape from this. So, that is why to avoid this, or this may work fine, this may not work significantly. So, we are having that alternate way. In alternate way, we go for the additional auxiliary holes. Okay. So, these auxiliary holes are provided, these are the auxiliary holes, these are the auxiliary holes provided between the main holes. You can see these are the main holes. So, one auxiliary hole is provided. So, this auxiliary hole basically create the cracking here in the top benches, and this will be blasted. So, what will happen? This one will be blasted first. So, this is first, then this is second, and then we are blasting this one. So, when this is being blasted, by that time this top part is already fractured. So, this part is already fractured. So, this fractured part will be easily thrown out by this charging process, and that part can be easily utilized. So, basically this has the drawback, it is incurred an additional drilling cost, which is a very difficult positioning of the holes and getting the blasting this one. So, that additional drilling cost is there, but these auxiliary holes which are very effective to fracture the top hard layer. So, that is a common technique to use for the top hard layer condition, and similarly we can have a clay formation also, or maybe hard formation also. So, in clay formation we have to avoid that part charging, and in this part we have to go for must charging at these hard layers. These are there, and this positioning of the layers are very important and must be considered while we are considering the rock mass impact on the surface blasting. We will continue the impact of rock mass on the blasting in the next class also. Thank you.